So I'm talking about robot perception for real life applications, and there's going to be like let's say, a 30 to 40 minute presentation. And of course, if you have questions, also feel free to ask them in the group chat, or so that we can answer them after the presentation. I think that's the most reasonable way in order to move forward here. First slide here. So the outline. So I would like to give you a bit of a motivation and context why we think that robot perception is important for solving real problems. I will introduce a sensing principle to you, which is a stereo system, and introduce a little of the benefits of that. I will talk a little bit about confidence and error modeling here, and I will give you an example also about pose estimation in SLAM, because in many applications, especially in the service robotics domain, the robots are usually not in fixed position. So we have two topics to tackle here. One is the object pose estimation or object identification, but also the robot pose location. That is quite important in these cases. I will show you a quick application of that and then come to my conclusions to the very end. What are the requirements that we see nowadays? First of all, I would say that the perception should be tightly coupled to the manipulation, because in the end, what robots do is they have to interact with physical objects in the scene. They have to perceive them, but also you have to be able to basically, in the end, manipulate them. Giving you a small example, if you want to detect a glass, for example, it's quite important what you want to do with the glass afterwards. If you want to drink from it or pour it, or if you just want to place it from one location to the other. So that depends a lot on then what you want to do, how you perceive the part, what is the important way of grasping it. So in my view, this has to be tightly coupled here. In terms of the software design, you have to have a modularized software that you can break down complexity, especially if you say that you have a complex system, you have multiple perception pipelines, you have a manipulation, and you want to bring that all together. So it's not good to have it in one program, but break it down in multiple reasonable bits and pieces, so that you can also achieve robustness and testability in the end. Additional to that, a quick adaptation to environment changes, especially in the service robotic day, is quite important. In the end, we are dealing for robot perception with the interaction of a vision system with a physical device such as a robot. And here you have a couple of issues in terms of calibration, time synchronization, and so on, which is like 90% of the issues you may have in such a scenario. So it's very important also here to have an easy integration into the robotic solution in the end and understands what's going on in the whole pipeline. Last but not least, as you may know, the expertise for getting a vision system, perception system up and running usually is quite high, and that actually limits the application of these systems. So people need to be able to set up a system without being a deep expert in it, and that's also one of the key issues that we are tackling here also at Roboception, to make sure that non-expert can use complex perception systems. My focus is on 3D perception. Just to give you 3 testimonials here. So there are quite known people that say, that the 3D vision is actually a disruptive technology that you need, especially for spatially structured environments. So the classical 2D vision is nice, but in most cases, especially when the objects are less known, it doesn't give you scale. And scale and distance is quite important for a perception system in order to, in the end, manipulate and grasp the objects. So this is somehow in the same pipeline. This is why 3D perception as such gives you a lot of additional information that you need when you're coupled with a robot. So machine vision can be done in 2D, but once you couple it with a real system, for sure the third dimension makes a lot of sense, also in order to react to changes in the environment when they are less structured. Also a quote here for when the first versions of the Amazon Picking Challenge, the guys that were handling it in 3D were clearly an advantage of it, because here you didn't have to deal so much with like the illumination, the distance, the correct scale of things, a little bit shifted a shelf or something like this, so that was easier to do. But you also have to see that the 3D vision itself, it brings another dimension. So in general, the system becomes a bit more complex. And a lot of the for the human, it's quite easy to deal with stereo and to adapt on it. But of course, for like a robotic system, that is something that even brings a bit more intense way of dealing with the scenario. Yeah, I'd like to show you a quick video here, which just shows what happens if perception goes wrong. So a slight inaccuracy in the perception, you want to place the object, and in the end, it may be a funny scenario, but of course, all of you who deal with robots, when you have a localization error, objects are not where you expect them to be, you grasp into the object, you smash the object, you basically tilt your robot. So when the 3D perception doesn't work, that's a very common result here. This is why it's very important to interpret the data not as the data itself, but also its confidence, accuracy, and reliability, because in the end, you're relying on a channel performing a task, and this is really important for you then also to make sure that you interpret the results as is. It's not a mechanical thing, like it's exactly 1 meter and a couple of centimeters long. It has to be a certain inaccuracy. Each vision system has that, and you have to deal with that in the real environment in order to make use of that technology. At Roboception, we are focusing quite a lot on stereo vision system, and you may ask why, and I'd like to give you a quick view on that, which we see here. The stereo system itself delivers, on the one hand, 2 images, and on the other hand, out of the same system, you can have directly synchronized in time and also calibrated in space a depth image that relates usually to the left hammer. So you take one shot and you get both. You get an image, you get a high resolution image, for example, and you also get a depth. You don't have this issue when you work with a laser, where you have the laser depth measurement and you want to align it with the 2D data. Then you have to figure out how the time synchronization is, how the spatial calibration is. So that gives you in one. Stereo is something that requires computing resources. With newest technologies also developments for the machine learning, you have a lot of resources more available than before. And for the depth measurement, you need for the accuracy, flexibility, and the images you can use for the machine learning. So you have both here. So I don't know many approaches that work well with machine learning in 3D directly, but what you can do easily is that you have the 2D image calibrated through the 3D point cloud, you do the machine vision in 2D, and you do the depth estimate and everything that relates to the action of the robot in 3D. This means that you can combine algorithms and machine learning in one system. So you can go with a classical system that delivers you an error in a metric error, but together with a vision machine learning system that usually provides accuracy in percent. And I mean, if you're working with a robot, it should be an accuracy in a metric scale, because otherwise you cannot really estimate how well you are detecting the pose. And this can be nicely done when you combine the two. Second big advantage is you can work with a high resolution image for the machine learning in case, and you can reduce the point cloud to a reasonable and computable way. So giving you Excel, you can have a VGA image, but the depth can be computed in VGA third or something like this due to computing time. So that's something that you can also scale and play around with. So it helps a lot in these kind of scenarios. Yeah, this slide is quite complex. It just shows you the whole perception action loop, and I just want to go into a few steps in that here. So if we start from the left, we have the scene registration. So we have a point cloud, we have color images, we have black and white images. Then we have to perform a scene interpretation, finding localization of objects with respect to the environment. You can make use of some simple algorithms saying you want to detect a plane. If you have tabletop scenes, you can do the clustering, you can do the object recognition, and you can also do pose estimation 3D and 6B, depending what you need for your application. That's like the perception part itself, but it also relates to a lot of other additional information. In many cases, you have an object model database which provides you with a CAD model, with a mesh or other information here. You may have semantic annotations that you can use for the action or other restrictions. You may have mass and inertial properties, and also maybe even graphs defined on these objects, which is quite common in order to identify what you can do with the object in the end. Addition to that, task information. So what is supposed to be done with the gripper? And this all is information that you may have in the background and can use it for your perception tasks, but also for the action that follows after. I'm assuming you want to grasp the object and manipulate it. For known objects, you can just go with a graph database. Then it's always nice to have like familiar objects, so from one mug to another. Or what you also quite commonly have, that you have to deal with unknown objects, especially in the logistics domain. You don't know what's in front of the camera. You just know it's an object of one kind in a bin, for example, but you wouldn't need to manipulate it and place it in a certain orientation. In addition to that, task information is important, where you want to go, how to consider the inverse kinematics and reachability of the manipulator. This means you have to do some graph sorting based on reachability, feasibility, and so on. You have a motion planning constraint, given the case you have just a single robotic arm. You want to have a collision-free path to the part. You have to consider collisions of objects with other objects, with the gripper, with potentially the bin, or even more complex environments. And then you end up in the grasp execution, and then the interesting part comes, because usually what you plan is not what you really execute. So it may be the case you grasp the object, it's slipping a bit, you use a suction gripper, you don't have the exact pose. So here, for a successful task execution, it relates to have a supervision of what you're actually doing. So checking again how the object is in the gripper, checking again, can you reach the target position with that, checking if you transport actually the part from position A to B. So a lot of additional things that you have to consider, and this is what I call the supervisory system here, which is quite important for a correct execution of the task. Maybe you also have to change some of the executions here. And then you need some kind of feedback from the perception system again to that part in order to figure out if you do everything correctly. Yeah, so the key questions that we can have based on that is that we are able to perceive the environment and we are able to adapt to changes. There's a world model considered. You need to have somehow the state of the world, because in many cases, from the robot perspective, you don't see the world at all times. So you have to keep track of the state, what's happening in your environment. You have to detect the changes in your plans and replan and perform the actions based on the capabilities, and also considering the uncertainty you have in your perception, but also in your action. On the research side, key questions from my perspective are that you have to represent the knowledge about the objects and their purpose so that you are able to determine the right action. You have to represent the context of the scene. I will show you a quick example later on why this is important. And you have to represent the uncertainty and deal with the supervision of the execution of the task. So that's the key questions that we should consider in that context. Giving you an example of why context matters. This is just a picture I got from a person called Joan Steiner. And it looks like a kitchen scene in the beginning, right? You look at it, and when you think it's a kitchen scene, everything is correct here. The human interprets the scene as is. When you look closer, I hope it's visible here on the screen for all of you, then you see that there's a lot of things in the scene that doesn't even belong in the kitchen. So if we go for the oven, if you come closer, you see that's a representation of a Walkman. So it is not even an oven in the end, but it's a different thing that just looks the same. If you look for basically the chicken that you see there, it is also just a nut. Or basically the tops, the things on the oven are just small little spiders. And if you come closer to that, you see that the context that you assume this is a kitchen scene really brings you to a wrong interpretation here about all the objects that are in there. So like a vision system without a context would have not identified any kitchen object in here. So this is quite important that you have the context of the scene, and this also shows you what happens if the context is not correct or assumed in the wrong way. So this is also something for the robot perception which is quite important to align where you are, that you consider your environment constraints, in what kind of environment you are. Is it a lab environment? Then you can cut down a lot of complexity. But of course, this assumption must be correct, because the robot will not perform the right task if you're switching context in that particular case. Just as a brief intro to that, I guess that is something that helps a lot to understand why the context really matters for a perception system. The sensors we use usually come from different areas. We have ultrasound sensors. They're quite common in robotics. You have like laser-based systems. You have cameras. You have stereo systems. You may also have time of flight. Some of the systems have a safety function as well, so that you can make sure that you're detecting the objects safe, which most cameras don't do at the moment. So you may have, for safety, also other constraints on the system. You may have omnidirectional cameras, which help you quite a lot to see the whole environment of a mobile robot, but in the end, of course, have some issues with how you calibrate them, how you get the metric information out of that. So that's always plus and cons with one sensing principle. This is why for most applications, people actually go for a variety of sensors. You may apply a SIG sensor for the safety for your mobile platform, and then you go with a camera to determine where the objects are, or something like this, or you combine a time of flight with a standard camera because you want to have a depth information that's accurate together with an image that comes from the camera. So in many, many cases for robotic perception, it's not the one sensor that you use, but it's always a combination of them, because each single sensor has a drawback that may be difficult for you, and especially the broader the scope, especially in the domain of service robotics, you have to consider more than one sensing principle. You have to fuse this correctly. You have to calibrate them to each other. So that's for a reliable system that's key here. And it depends what you use. Really depends on where you are. If you're outdoors, if you're indoors, if you have areas where there's a lot of plain and white surfaces, or if you're in an environment that is nicely structured in that sense. So that really depends. And this is why this belongs to the selection of the perception system, to envision the field of application of your system. Before you start working all the algorithms, also check on what kind of sensing modalities you want to use for that specific application. A key aspect or key system that we are using is stereo matching, and I would like to give you a quick introduction into that, the principle, how it works. It usually runs through 4 steps, which is the acquisition of the stereo images. You have a left camera and you have a right camera, and based on what you see in the one and the other camera, you can determine basically the distance that the objects in the end have. You have to do a rectification of the data. In most cases, you have to match what you see left to right, and then you have to perform a triangulation in order to determine the depth. As you may see, the triangulation is based on the distance and the base distance in between the left and the right camera. So this already shows that the further objects are away, the less accuracy you have on the depth measurement. For the human, for example, we have like a base distance of approximately 6.5 centimeters. That usually leads to optimal stereo range up to 1 meter. That is actually more or less the range that our arms have. So this is how this system, our system, is designed in the stereo case. All the other information that we usually draw don't come from stereo, but from the motion of objects and the interpretation that we put into that. For the rectification of the camera, there's usually a calibration that needs to be done. So you have intrinsic and extrinsic parameters such as distortion, the focal length, the height, and the width of the pixels. And then you have the translation and orientation between both cameras. So for the extrinsic, so this is something that belongs to each of the stereo systems. You can see in the small image to the right. So if you have the left camera, you can have like a translation of the right camera to the left. You can have a rotation around the visual axis. You can have a tilt, and you have multiple other turns. That is basically the extrinsic stereo camera parameters, which you have to determine in order to make use of the depth estimation. And then you are projecting usually both images on a common plane. And the idea here is that you have the epipolar line. The epipolar line is basically the viewing line that if you have a point in space in the one camera where this is projected to the other camera plane, you want to do that in a way that the epipolar lines are parallel to the image rows, because then you have to look for a feature from the left camera only in the same image line on the right. And this also leads to that the corresponding points have identical vertical coordinates in the left and the right image. So on the one hand, you see below that we are basically doing having a raw left image here and the rectified image here, and you can see that these lines become parallel then if you do the rectification. If you then add the second camera in the right distance on the same line, then you find nicely the one feature in the same row as the other one. The matching is actually the most important step here for a nicely functional stereo vision system. So what you do is basically you're looking for correspondences in the left image to the right image. You see that this is nicely done if you have these kind of edges where you, this is the upper case here, where you basically have this corner here. This corner can be nicely aligned with a corner in the right image, but you see it is difficult where you have like a point here on the plane that could correspond to multiple points here in the other image. And the key challenge for the stereo matching method is to make sure that you match basically the right point in the left image to the right point in the right image. And this is where it differentiates if you get a dense depth map or something that is mostly working on edges or something like that. We are usually applying the semi-global matching algorithm. By the name, you see that it's a global part and it also has a local part. So the best algorithms usually are working globally, which means that you want to build a corresponding between the one point in the left image to all other points in the right image. Of course, this is computationally quite intense. What we are doing here is basically that we reduce the whole image to 8 passes. So if you check for the pixel of interest, you usually don't take the full image, but you're taking passes through these image towards this point. And these values you keep in order to figure out and use that as a matching post. That has a locality, is quite local, so it's not like a correlation-based algorithm that's looking for a window. It is on the point, but it applies also a global approach because it considers the whole image for the computation. So basically the output of that is a disparity map. So that is the horizontal pixel offsets of the corresponding points between the left and the right image. So basically this is the coordinate in the left image, which is x, and then you have the distance to that pixel x dash, and the difference between the two in pixel is actually the disparity. So basically by default, a stereo system gives you a disparity. Based on the calibration of the camera and so on, you can then compute the depth out of it. But the base information that you get is always a disparity, which is a correspondence to the depth later on in the image. In many of these stereo processing, you have invalid values. So this usually happens in some scenarios here. You can assume you have the left camera and you have the right camera, and they see the scene from different angles, different viewpoints. This is why here you're having some missing parts when you have like objects that occlude each other, where you don't have any texture. Of course, to the left, you have no image overlap because you assume that you go from the one image to the other. You don't see always the full scene. And also you have some missing texture sometimes, which you can see here. So this is where the stereo algorithm doesn't perform. So three issues occur. The images do not overlap, then you don't get a depth image or disparity image here. You have occlusions that avoid you to see the same scene from the one camera and the other camera. And you have missing texture in the image scene that doesn't allow you for doing the matching. Usually there's a trade-off between resolution and frame rate. As you can assume, the whole stereo algorithm is quite computationally intense. So just an example here, you may have like a VGA resolution at 3 Hertz. You may have half VGA at 15 Hertz. And you may go at 225 Hertz in VGA third, just as an example. So you can scale actually frame rate by reducing the disparity image or the depth image resolution, which you usually have to do for all kinds of applications that apply stereo. Then how do we get from the disparity in pixel to the depth? This is how we apply the triangulation, and the triangulation happens by using the image coordinates with the focal length in pixel. You apply the disparity value, and then you just basically use the stereo baseline in meter, and based on this two information, you can compute the depth. So this is also the focal length of the camera is quite important for that. The disparity value is that the parameter that you get from the matching. And the stereo baseline is a fixed parameter that you get from the physical properties of the system. So the upper two, F and T, they're usually fixed, and the disparity value is that what changed. Here you can also see why usually when you apply stereo, you don't want to go with like autofocus cameras or something with a variable focus, because then this upper part here is not constant anymore. And this means that you have to calibrate new for each of these settings, and they have to remain stable. This is why it's not recommended to use zoom or other changing parameters on the camera itself. Usually you go with fixed focus lenses here in order to make sure that the system operates over time in a reasonable way. Now we come to the evaluation of the data. So the disparity is an estimate. You can see it based on the matching and all that stuff. And the errors that are included in that can be done by the discretization of the pixel. You go always bit pixel by pixel, so the pixel size somehow matters. When you want to have a fine accuracy, you have mismatches, and you also have noise in the individual camera pixels. So you have basically here in the scene, you have the left image and the disparity image to that. And what we come to now is basically that you want to compute an error image, but also a confidence image, which tells you how reliable the data is measured. That comes back to the point when you apply an action, it's really important for you to know, can I trust the data or not? And how much can I trust it? And this is not only related to the error that you come with plus minus 5 centimeters or something like that, but it's mostly relevant based on the data itself, because this applies to texture and other factors in the scene. The error and confidence are usually provided in pixels. They come at the same frame rate and resolution as the disparity image, and usually the disparity error is in the range of 0.5, 1 or 2 pixels. You can compute that to depth using the formula that we already seen. So you're putting the disparity error there, you're having the focal length, you're using the stereo baseline and divided by the disparity value squared. And this is how you can compute the disparity of error over distance. as you can see here. So here's two examples. We go with a 65 millimeter baseline and a 160 millimeter baseline. You see that it's a quadratic function here, and that the depth error increases over distance quite a lot. So given the case, we go with the 65 millimeter baseline. At 1 meter, we already have a disparity or depth error of 10 millimeters. So this is why also you should decide on the baseline of your system in order to determine what kind of physical error you already have, just because of the disparity error that you're assuming. And this 0.5, 1, or 2 mostly relates to the good accuracy, the good calibration of your system, or also the way you selected the lens, and then so on. So all the physical parameters are behind this disparity error that we are showing here. The confidence is basically a probability. And it shows you that the true value is most 3 times the disparity error away from the measured value. It comes from 0 to 1. And what you need to check here is then both, actually. So you check if a high confidence there but a large error. That is usually something that is where you have low or weak texture. Or you have errors where you have a very low confidence and a small error that says that you have sharp and good texture, but it's globally ambiguous, so a repetitive pattern also. This is why you should see the error and the confidence always together in order to decide if you want to use that value or not, because the one tells you a different story than the other. So the confidence is basically a pattern indicator, so to say, and the error is usually like a texture indicator. So that's basically what you can take as a message from that. On top of that, you can add other options such as filtering, where you go for min-max confidence or something like this. You can apply hole filling to it. You segment areas out of it. You smooth them. And you can do a noise reduction in case you just take a lot more images. So basically, the static scene allows for averaging about images, and you reduce the pixel noise. That is something for static scene. So there's a lot of other things that you can do on top. And that's actually also parameters if you do stereo matching with machine learning. There's these heuristics that you can put on top that the neural network looks for you. So basically, you have the scene, you have a couple of representatives, and all these heuristics that are listed here are the parameters that your neural network will figure out in order to really, in the end, close the scene and get a dense depth image. This is why if you're using like machine learning for stereo computation, you should be careful what kind of data you put, because you need to really figure out all of these parameters and see that you're giving it the right data in order to being able to get the right representation of the scene. Especially the hole filling is something that's quite dangerous because it can be that there's really a hole, and then you don't really figure out that these small detail that you're actually interested in is not seen anymore in the depths. So also here it helps a lot to combine the 2D and the 3D in that case. Giving you an example here, like a quick video. So here we are putting to the upper left the camera image, the disparity image, the error image, and also the confidence here. You see that we have some sharp edges here, which give you a high confidence. We have here an area with relatively low visual texture, which gives you also a low confidence. And here you can see also the combination. So the wider things are here in the confidence, the more confident the system is. The lower they are, or the grayer they are, the lower the confidence. That just gives you an indication on that. Good. So now we figured out a way how to determine the distance of the objects. And the second step that we are doing as a base algorithm here is now how we determine using a camera where we are in space. Especially for mobile robot application, as I said, that's quite important. What we are doing is basically we are combining the camera system with a visual odometry, and we are fusing that with an inertial measurement system. This helps a lot to compensate for image blackouts and other stuff. So the IMU for pose estimate, as many of you may know, is not very reliable because it starts to drift in an instant. And this is why we are basically compensating that with the visual odometry. The IMU compensates for fast movements. The visual odometry gives a more constant way within the frame rate to determine the pose. This is a so-called dynamic state estimation or ego motion estimation, so the terms can be used vice versa. What do we do in a visual odometry? So we have here, and in this case, we're talking about the stereo-based visual odometry. So we are computing actually not only the feature, but also the depth as a feature. It's kind of a sparse stereo, as you may call it. So we have here like 3 reference points. We're taking them from different views. We're taking them relatively to the pose A and pose B. And as we can measure the distance from view A and view B, we can easily then determine also in the both view the upwards motion in between these features. It's optical flow. The assumption here, and this is a quite strong one, either you move the camera or you move the scene. If you move both, it doesn't work. So here we are moving the sensor. This means the scene has to be static. Quite important to notice, because if both things are moving, then the estimation will not be correct. The motion estimation is based on the characteristic points. If you're standing still, basically nothing is happening, the scene is static. If you're moving from A to B or up and down, you can see that the features are moving, and then you basically between that scene and the other scene, you see a distance, and this is basically how you can determine then the motion of the camera. It's relevant to have a data fusion principle here. So you incorporate data from the visual odometry, the VO, the IMU, and as you may know, the more I proceed with a visual odometry, even if it may be based on an IMU, we are accumulating error over time. So basically, all the pixel noise, everything that we have in the system, the error accumulates. So that means like a visual odometry is quite accurate in the beginning, but it's getting less accurate on the position, even if we use a lot of other issues like estimating also the gravity vector and the conformation of both to each other. The big advantage that we have when we're using an IMU with a visual odometry, the visual odometry usually has a frame rate that is low as opposed to what an IMU can do. So for a high dynamic system like a multicopter or a flying system or a quite fast mobile robot, the IMU compensates basically for the latency and the low frame rate that you have in the visual channel. And this is why here for a mobile robot that is driving quite fast, it is very important to fuse the two things. So the dynamic state is basically comprised of translation and orientation, which is a pose, but you're also getting a lot of other information like linear velocities, angular velocities, and so on. So the pose is basically the translation and the orientation. You can do this image aligned with a high accuracy and a low frame rate. You can do this more or less real time when you go to the, let's say, the IMU runs at 200 hertz. You have a low latency, it's less accurate, but you're relying the data on the faster system. So if you go to the visual odometry as the base, you have a lower frame rate. If you go to the real-time pose, you have a smaller accuracy, but a higher frame rate. So basically, the odometry can be, or pose can be determined in a different way. The linear velocities and so on, you mostly get from the IMU directly, so this runs at the 200 hertz. So here you also again have the choice. We can be in between accuracy and real-time. So also for you to understand, if you want to move a mobile manipulator with a visual odometry and you're using that as a pose signal, you probably want to go to the high frame rate. If you have a mobile robot that is running over long distances, you probably go for the image aligned and using the lower frame rate in order to have higher accuracy and accumulate less error. For this here, you can do the navigation or the object modeling. And as I said, for the low-level control and highly dynamic system, you go for the higher frame rates, as already said before. Giving you an example how that looks like. So basically here we are moving the camera, the stereo-based camera of the RC Wizard around the object. We are using the visual and inertial odometry to compute the pose based on the image. And this is how we can generate the point cloud without any additional pose information that we get. So that is the application, especially if you have like a mobile robot. You may use the wheel odometry or something like this as an input to the system, but you can determine the pose itself without any additional information. I mentioned briefly SLAM already. So as I said, visual odometry accumulates error over time. In order to compensate for that, many people apply SLAM or online SLAM in our case. This works basically that we are figuring out features that we recognize while we are traveling. Of course, this only works when we are really closing loops. So if you have a mobile robot that goes like 100 kilometers in one direction only, SLAM doesn't help you. It only helps you when you return and close a loop. And at the moment you come back to the place you've seen before, then you can say, hey, this is the same feature as I've seen before. It is in that position, and then you can reduce the drift error that comes from the visual odometry based on that. As you can imagine, if you computed a stereo map or an occupancy grid based on that, also that has to be corrected, because of course if the pose was drifting before and you compensate for that, you have basically a jump in pose. A physical system doesn't jump, so that basically has to be considered in the algorithms here as well. But it is a short circuit in order to make sure that the estimation error is reduced and the uncertainty overall system is reduced. Also here, you can use error and confidence of your system. So basically, if you're going with the so-called Octomap that just builds on top of the 3D data directly, you have a lot of uncertainties and also quite noisy map. If you're using error and confidence from the stereo, so you know where you are, you know that you have certain errors in the 3D data, you can generate a much better 3D environment of the world. You still have issues here due to drift and other topics, but the map will be much cleaner and better afterwards if you consider the trust in your system in generation of the map. This gives you also just a quick example how this looks like when we are driving in a parking garage here. Here we are manually moving the robot. We have the depth, we have the accuracy, and we have the confidence from the scene in a quite low resolution. We're building that in a 3D environment here. And you will now see that this is a confidence representation where the map is updated based on the confidence values, changes constantly over time, and improves basically the map that we've generated in the first case. So that is also something that can really improve the overall performance of the system. Sure. We have an application video that I wanted to show you. So the task here is that we have a distribution center. We have a central position where we are distributing the goods, and we are using a mobile robot here in our office to basically send around the individual items. The items that we are dispensing here are apples, and the task is so the people in our office, they have an April tag where they are sitting. This is the goal position that we want to go for. And then we are creating a map of our office. And in this map, the robot has to basically deliver the apples to a certain position. On another station, we are then using another robot that picks the apples, places them in the mobile robot, and basically delivers them to the individual person. And what we are doing here is picking of unknown objects. So we are not having any model of the apple. We are mostly doing a segmentation in the bin to find 4 grasp points for the suction cup here. Our colleague here just asked for an apple. The robot is going to that automatically based on the map it has. It's using also the 3D information it's generating to avoid collisions. As I said, there are no laser involved here, so safety is not fully considered, but for such a small system, that was not the key target that we were aiming for. And then the system is able to bring basically the apples to the target position, deliver it, and the person can pick it up. The robot is then returning to the filling station, checks how many apples in there. We'll use some text here as well for that. Using a clever combination of text and unknown objects, so to say, gives you a good way and how to move forward in such an environment and to deliver basically the goods to different positions. So you can see here that we are going to the next station, we're taking another apple out, the robot is moving on, and at some point is getting back to the refilling station to pick up basically more apples here, which is then goes below. The robot has two cameras. One is looking into the bin, the other one is looking at the robot. Once it sees that the robot is back and has empty spots, the picking robot here continues to fill up the robot with new apples. That's basically something that we did in the frame of a European project here as well. It all comes in ROS, and this is what was the scope of this project. Yeah, I mentioned a little bit that it should be easy to set up a system, just one view on that. So here we provide a web interface for configuration and calibration. That helps a lot to get direct feedback. People are nowadays used to these kind of interfaces. So usually no coding is required for calibration and configuration, which is quite an advantage for such a system, and also for the acceptance in order to bring such a system into the operation. Most important functionalities to offer is hand-eye calibration, because that is something that always has to be done. So the relation in between the camera and the robot, for that there needs to be a clear tool and some kind of self-calibration of the system during operation to check if it's still in the right status. So these are the two things that we consider quite important as a functionality to be offered to people using perception system, besides the time synchronization. This leads me to the conclusion of today's talk. So the 3D perception is actually the key for mastering these everyday tasks. And I would propose that stereo vision for sparse and dense data can really be a big part of that, because we have both. We have depth, we have images. Images are used for multiple things. There's also easy for the human to understand image, much easier than what happens in the point cloud. So it's also a matter of interaction with someone. And you can scale the depth and the image resolution independently from each other to also optimize for computational time. So this really is something, especially in the age of machine learning, that helps us a lot to tackle all kinds of recognition tasks with robot manipulation, which requires distances. Consistent confidence and error modeling is needed to be done for a decision-making system, because if you want to really implement this perception action loop, you need to be sure how much you can trust the results. So it's recommended not only to deliver the data, the output, but also the error and confidence, so that the next system can decide on how much to trust the action that was taken before. I'm a big fan of combining for object detection classical and machine learning approaches, because it combines the best of both worlds. So in our case, the machine learning helps us to reduce the parameters the human has to tweak, but the classical algorithms gives us an information in a metric system, so we can use it as a standard error that people can understand and estimate. Because if you have an object detection task and the algorithm tells you it's going to be detecting that by 99%, how do you judge that? If the algorithm tells you the accuracy of the detection is 1 millimeter, then you know something that you can use for your later application. And this is why these two methods should be combined in order to get a human readable result in the end. Machine learning based picking and applications, I would differentiate between two. So one with offsite training and without labeling, and then the data-driven and on-site training. So it always depends on the data you have, and usually in the robotic domain, we have small data and not big data. So I highly recommend to make use of virtual training, so not data, but model-driven approaches that you train your objects in a simulation ahead. I think that's the right way to go for us in robotics, where we don't have enough data available, because it's really hard to tell people to record data, label it, interpret it. So we should make use of model data that we have also in virtual training environments. And then most important also for the, not only for the action but also the action supervision. And that's something that as robotics researchers, we should care for a lot, because this in the end gives us reliable and trustworthy systems. And this is what, when we deal with people that are doing in service environments, they need reliable and trustworthy system. And this is why I think this action supervision is the next big topic to tackle, where we all should be working on. And this ends my presentation for today. I hope you have a couple of questions that we can answer in the next, let's say, 5 minutes.